Hello everyone. As introduced, I'm Jung Choi, working in the W department. And today, I'd like to talk about the spatial audio involved with the transformer models. So before to begin my talk, I'd like to shortly mention about today's event, how today's event were organized. I firstly heard about today's meeting in Sydney last year from Professor Sung Young Kim, but he didn't provide much information to me at the time. First of all, he didn't mention that I'll be talking in front of 100 people. And secondly, you didn't mention that I'll be speaking in front of my academic advisor. So, in this place, we have the great Professor Yang Kim sitting over there. And I really feel like speaking in the lab meeting as a student. Okay, so anyhow, let me introduce my lab first. Now I'm a professor, so yeah, this is my lab, and it's called Smart Sound Lab. We have the listening room, anechoic chamber in this building. So my office is just on upstairs, and these are my students. And as you can see, we have what is the laser point here? Yeah, okay, they are working for many different topics. And especially the topic I'd like to deliver today is mostly done by Dong-Han Ri is here. So it'll be about the sound source localization, not localization, sound separation and speech enhancement, and also done by Da-Yun Choi. Okay, so what I'm going to talk is about the AI understanding the spatial audio scene. So when we talk about the spatial audio, let's skip this part quickly. We can focus on some sound object that can be easily localized in one place, or we can be interested in the ambience, such as the reflected sound and the reverberations. But we all know that spatial audio is formed by very complex physical phenomena, such as the propagation of the direct wave, as well as the sound reflected from the walls. So there are basically three important factors that determines the quality of the spatial audio: the user and the sound object and the surrounding environment. So the AI model I'm going to introduce today is also about this environment and sound object, but not the user, unfortunately. So let's think about, we have this auditory scenery here. One listener is hearing the sound here, and there are several sound objects, multiple sound objects producing the sound simultaneously, right? And there is reflections from the wall, so it'll be a very complex problem. So I think Professor Park, Yong-Ah Park, already introduced the difficulty of the cocktail party problem, right? So today I'd like to provide the solution for that, how much we can separate the sound captured by multiple microphones in this complex situation. So the ideal goal, ultimate goal, will be separating this mixture of signals such that we can find out we can hear individual sound sources, as well as finding out the class and finding out the direction of arrival or the location of the sound source. Okay, so that all of these topics belong to the audio scene analysis, in short ASA. So my interest is with these issues. The first one is the audio enhancement, meaning that we have very reverberant and noisy signals, but we want to remove all the noisy signals and reduce the reverberations, such in order to have very clean signal. That's the enhancement. And second one is the separation, separating individual sources of signals. And third one is already introduced by Professor Park, the sound event detection and localization. And recently, target sound extraction task is becoming also popular. It is about the extracting the signal, certain signal that is correlated with certain clue we provide to the AI model. For example, if we provide the class as a clue to the AI model, it only extract the piano signal from the mixture. Or we can think about the DOA as a clue. If we want to extract the signal only coming from 30 degree in azimuth, then it can subtract certain signal. Or we can provide similar signal the signal similar to what we want to extract. Okay. So that will be the topic I'd like to deliver today. But as all we know, we have a very special functionality or special ability to do this kind of task. For example, if we have a clear DOA separation, directional or label separation of the sound sources, we can utilize that information to extract the signal, or we can make some kind of information fusion between DOA and audio pattern or the class, right? The type of the signal, I mean. So how can we implement AI model that can make such kind of information fusion? So in order to do that, I'll be talking about the transformer model. But before to talk about that, let me shortly mention about our auditory process. First, if we have this kind of two-dimensional spectrogram with respect to time and frequency, then our brain can extract some kind of basic features. Features means some properties such as pitch, timbre, or it can be the directional label of the sound source or the distribution in space. So this is the basic feature analysis stage. And then our brain can utilize those informations to form some kind of correlated groups in order to separate the sound signals. So my talk is about how to make such kind of fusion of these basic features to separate the signals. So yeah, again, it's a very complex task because these multimodal features are very different in the matrix size. The signal types are very different. So we have very heterogeneous features. And of course, the environment are diverse. I mean, the room we are playing the sound are all different, right? And the person who is making speech are all different. So we have very wide range of diversity here. So first problem we have is the diversity of the source signals. We have many different source signals, and the environment are all different. The shape of the room are all different, and the array can be also different, right? So practically we are using many different configuration for the microphone array. So ultimate AI model should be able to be compatible with all the environment and all array geometry and all source signals. But I will focus on these two topics. So how can we implement environment agnostic AI model and array agnostic model? Okay. So transformer. Why transformer? Transformer is quite popular in the language processing model nowadays. LLMs are all using the transformers. And ChatGPT, GPT means generative pre-trained transformer, right? So why transformer? Because transformer is specialized in finding relations between the data. So it comes from this language model. So if you think about the language translation model with the source language and target language, then transformer model can apply some kind of a self-attention to find out the relative importance of the words to make a prediction or the translation to another word. So we will utilize this relation identifying ability to solve the cocktail party problem. Okay, so it's characterized by this multi-head attention mechanism. It looks complex, but the essence of this algorithm is to produce three different instances called queries, keys, and values from a single signal. Not a single signal, it's a multi-channel signal, but from the same signal, we produce three different instances and apply the attention mechanism to that in order to find out the relation. That's the key of transformer. So for the audio signals, we can also first build up some kind of input sequence. So here sequence is something like a word in the language processing model. We have a sequence here. So from the auditory spectrogram, we can build several sequences with respect to time, or with respect to frequency, or with respect to microphone channels. Okay, that can be done by several convolution models. Once we have a sequence and the embedding for the vectors, then we can apply some linear projections to build up the query key and values and find out the relations and develop filters, adaptive filters with that. Okay, so how it is being used to realize the environment agnostic enhancement model. The first task I'll be mentioning will be the audio enhancement model, especially for the speech. But no, this is just the enhancement model. In the past, we used the convolutional layers to develop this audio enhancement model. It showed quite interesting result, but if you hear this, so you can hear the bird chirping signal, but with the noise, right? So after removing all the noise, so this is the audio separated by AI. This is quite not bad result, but the problem was that if we change the environment, then it collapses. I mean, if we train the model in this room and test in another room, the performance rapidly goes down. So it is not the environment agnostic model at all. So we decide to use the transformer. So I'll skip the detail. And our first transformer-based model is called DeFTAN. So DeFTAN stands for the Dense Frequency Time Attentive Network. So it generates some mask for the complex spectrogram acquired from multi-channel microphones. So M stands for the number of microphone channels. So after applying this mask generated by AI, it separates a certain signal. In this case, it can be speech or the single target signal. And this DeFTAN utilized the transformer in this way. First, it pre-processed the spatial information with a dense block, and we apply the transformer in the frequency direction. So it's a frequency transformer, and then we apply the transformer for the time dimension. So it's a multidimensional transformer. So please let me skip all the details because I don't have much time. So when we introduced this transformer for the audio separation, and we tested over 2 different data sets, one called DNS challenge with a high noise, and the other is the specialized Wall Street Journal CAM0 dataset that has a lot of reverberations. And in this training and testing dataset, all the rooms were random. Each size were random, and the reverberation time were all different by changing the materials of the room. And the noise was also different depending on the samples. So when we trained the model and tested in another room, unseen room during the training, this is the noisy speech. You heard the speech, right? Yeah. But after the enhancement,
as in Kant, a loquacity which comes.
So yeah, it's doing even better than human. So even when the situation noise is much higher than the speech signal by 16 decibel, it can completely remove the noise and leave only the speech. And how about the reverberation? I mentioned that I will remove the reverberation as well. This is the noise and reverberant speech. And after the enhancement,
laws as the water vapor of the air, the gaseous vapor of the.
So this is the performance I've never experienced with the classical beamformer. I worked for a long time with the beamformers, but yeah, it's time to escape from the beamformer. And how about the reverberation only?
As the Commission heard in
it has noise as well, right? So yeah.
work outside the fishing industry. As the Commission heard in
This might be the one with only reverberation.
The dollar was particularly weak against the yen because of a recent decline.
And the reverberation.
The dollar was particularly weak against the yen because of a recent decline.
Yeah, it's really nice. Yeah, so if we compare the performance of our model with other deep neural network based models, the convolution based models, UNet based models, and triple path network, and so on, our single model outperforms all the predecessors, and our two-stage model is even better, the two-stage model of the previous one, in terms of the signal to distortion ratio, as well as in terms of the perceived quality. Perceived quality of the speech is measured by PESQ measure. It outperforms all the conventional models as well. And now this is an open source model. We released the code. So if you're interested in, then you can download from the web and freely use that. That means we have a better model now. Yeah, that's why we released this model to the public. Next, we developed a real-time version of this model. You know, in order to build a real-time model, we have to satisfy the causality, right? We only have to use the past data to predict the future, and the latency of the processing should be less than 20 milliseconds according to the requirement of the fifth DNS challenge. And the real-time factor, meaning the calculation time compared to the length of the signal, should be less than 0.5. So our DeFTAN-RT model satisfies all these requirements, and compared to these other real-time models, its signal-to-noise ratio, performance, and the PSQ are all great across different datasets. Each performance is 3 decibel lower compared to the non-real-time model, but if you regard the complexity, time complexity and space complexity of our model, this RT model is quite lightweight. Okay, so is it good enough? Actually, there is one dimension missing with the transformer. I mean, with our DeFTAN model, the frequency and time information is processed by the transformers, but not the spatial one, right? It's processed by conventional dense block. The spatial information could be also processed by the transformer, right? So before to using the transformer for the spatial dimension, we made some kind of modification and released DeFTAN-II last year. Release means we wrote a paper and submitted, but not open source yet. So let me skip the details. We use some kind of two-dimensional patching method instead of the single dimension vector. We use this patching to consider the time and frequency at the same time when we process the spatial dimension along the spatial dimension. And its performance is the state of the art now. These are the models proposed by Meta, or now Meta. It was the Facebook Reality Lab before. In 2021 and 2022, these models are now beaten by our model. And before DeFTAN and DeFTAN-II, there was another submission from Carnegie Mellon University in 2023 with this model. That was the former SOTA of this speech enhancement model. But now our model is much lighter and performance is also higher. Okay, so you can hear the demonstration in this link. And this model actually very nice. I don't know how much time left for me.
Some of his investments may never be found because they are abruptly disguised and buried in layers of ownership.
It's already passed, right? Yeah, but not because of me, right? Okay. Okay, so no, because of our passion, right?
Some of his investments may never be found
So
because
this
they
is
are
the
adroitly
de-reverberation
disguised
example.
and buried in layers of ownership.
Yeah, so as you hear, now the performance change is less audible because already high. It is already high, right? And this noise speech. And after the enhancement,
rose up again and began to fight afresh, and they fought until the place was violent or blind.
you don't
and they
need
had
to
each
hear the
7
clear
great
speech,
windows.
right? Clear
What night are
speech,
you
right?
asked following this?
Yeah. And let's move on to the separation. If multiple speeches are in the same scene, then we can also separate the speech based on the spatial information. So if we have these mixtures,
Numerous works of art are based on the story of the sacrifice of Isaac. Period.
by the way, we are using 4-channel microphones, microphone 4 channels in the link configuration. So yeah, it's not that many. So after the separation,
Numerous works of art are based on the story of the sacrifice of Isaac.
okay, and this is the speech 2.
Gillette is again a target of a major corporate raider, period.
Okay, again, these are tested in the unseen room during the training, right? So rooms are completely different. Okay, and at this point, we begin to observe some interesting phenomena. Actually, all these demonstrations are based on the simulated room impulse responses. But for some reason, we have to test this in the real venue. So we brought some microphone here and placed the 2 loudspeakers in a different angle from the microphone. And actually, we simulated the room impulse response with a microphone array with a 10 centimeter radius. But this actual experiment was done by 2.7 centimeter radius. So it's a completely different array from what the AI model is trained. Still, the AI model can work with a unseen array as well. So this is the noise and reverberant speech. Okay, and this is the next one.
Worse, or assets minus liabilities, widened at December.
Okay, so we also tested with the unseen language in order to check whether there is a language dependency, because this model was only trained by the English language. But what will happen with the Korean language? So if we enhance this noise speech, then its result will be
우리들은 일상적인 삶에서 기쁨과 즐거움
it's still okay, right? So it was really interesting because the array in the classical beamforming, array geometry is really important. If you change the arrangement of the microphone, then all the man-made algorithms will collapse, right? So in order to check whether our model has true array agnostic performance, we did some experiment with our DeFTAN-II model. So we trained the model using this ring microphone array with 4 microphones, and we changed the configuration, the shape of the array from linear, random, tetrahedron, right, in 3D space. And the performance table shows that it can still enhance the speech irrespective of the reference microphone array and circular microphone array with a different radius and other microphone arrays. Performances are all similar. So beyond that, we wanted to check we wanted to develop a model that's also agnostic against the number of microphones. All these microphones are 4-channel microphones, right? So what if we change the number of microphones? If the AI model identifies the relation between the channels by itself, it should be able to adapt to a changing number of microphones. So yesterday, I revised the paper written by Dong-hwan. So I cannot release our model yet, so it's blurred, right? But the key features with this new model called DeFTAN-AA is that it utilizes the sophisticated spatial transformer to extract the spatial relation. So now the transformer can adapt to different number of sensor microphones in the array. So when we are using 2 microphones, the performance are like this. 4 microphones, slightly better. It's natural to have a better performance with the increasing number of microphones because we have more information, right? But this model is only trained with 4 microphones, but it can still work with 8 microphones and 2 microphones. Okay, so yeah, that's what the transformer does. And finally, I'd like to let you hear our universal audio separation model. So previous model was optimized for the speech signal, but now if we have variety of the signals, then we can also separate these unseen signals, and it still works with the SDL of 13 decibel. So meaning that we can improve signal to noise distortion ratio by 13 decibel. So yeah.
Is the bundle and you never used to be crossed in. Out.
So we have 4 signals as a mixture in this noisy clip, and after the separation, oops.
Is the bundle opens up to be crossed in. Out.
There is a slight mix with others.
And you never used to be crossed in.
Okay, so the performance is not as great as the speech enhancement, but it's usable, although we have some very slight artifact. Okay, and target signal extraction finally. This is an ongoing work, so we provide a clue, the class of the signal, in the middle of the DeFTAN blocks. So after the target signal extraction, so yeah, this is the mixture of the 2 signals, and after the separation, okay, so this is my take-home message. Long live the beamformer. Now it's the era of the transformer. So the beamformer is gone. So yeah, that's all of my talk. Thank you for your attention.
Thank you, Professor, for that excellent presentation. We would have time for questions, but due to the time limit, we'll just go right to the break. So